If you hold your thumb up in front of your face and look past it at the wall on the other side of the room, you can easily demonstrate what parallax is. Close just your left eye and note where your thumb appears relative to the object on the wall. Then close just your right eye and observe again. You will notice that your thumb appears to be in different places relative to the wall when viewed through your left eye, then your right eye. This is because your thumb is near you and the wall is far away. This phenomenon of near objects appearing in different places against a backdrop of distant objects when viewed from different places is called parallax. You're all familiar with parallax error. This is where you get an inaccurate reading if you do not view the measuring instrument along a line perpendicular to the scale. This type of error is possible because the object or the indicator needle or whatever is closer to you than the scale is. However, parallax is not always a problem. We also observe parallax with our nearby stars. They too appear to move against the backdrop of the distant stars when we move our viewing point from one side of the sun to the other, which we do every 6 months. Over the course of a year, you will see the nearby star move from one side to the other against the backdrop. By observing the position of the star relative to the distant, apparently stationary stars over the course of a year, you can find the two extreme positions and measure the angle to the star from the vertical, that is, the line going straight overhead. This angle is called the parallax angle of the star. Remember, only stars that are near us in comparison to the very far away background stars will have a measurable parallax angle. Further away stars have such a small parallax angle, we don't have the technological capability to measure it. Even our nearest star, Alpha Centauri, only has a parallax angle of roughly 0.00021 degrees, which incredibly we can measure. Which brings us to, in the same way that an hour is divided into 60 minutes and a minute is divided into 60 seconds, we divide a degree into 60 arc minutes and an arc minute into 60 arc seconds. This means that 1 arc second is 1 over 3,600ths of a degree, which is, not rounding, 0.00027 degrees. So converted to arc seconds, this means that Alpha Centauri's parallax angle is 0.76 arc seconds, which is a much more user-friendly number. Going back to this diagram, we can now work out the distance to Alpha Centauri using trigonometry. You can see that this angle here, these angles here, are also the parallax angle. Using one of the right-angle triangles, we can see that tan alpha is little d over capital D, where little d, remember, is the distance from the Earth to the Sun, and capital D is the distance from the Sun to the star. So for Alpha Centauri, we find that its distance from us is 4.3 light years. If you're thinking, what about stars that don't make right-angled triangles at their furthest positions, and because their orbits are slanted compared to the distance to the star, good thinking. The reason we ignore this is as follows. The difference, if you think about it, between these two distances can be is 2 AU, and that is only 3.0 times 10 to the 11 metres to 2 sig fig, which is this, and the distance to the nearest star is 4.093 times 10 to the 16, so this won't make any difference to our calculations unless we can do better than 4 significant figures. Because we know the parallax angles are extremely small, we can now write this and this. It was decided that a new unit of distance would be created for the very large distances that you get for capital D. It was decided that if alpha is measured in arc seconds and little d is measured in astronomical units, then capital D would be measured in a new unit called the parsec. The distance from the Earth to the Sun is always 1 AU, so this means that a star with a parallax angle of 1 arc second is exactly 1 parsec away from the Sun. Or put another way, Let's try a very simple calculation here. A star with a parallax angle of 0.50 arc seconds is 2 parsecs away. To convert 1 parsec back into metres, just put metres and radians back into the formula. 1 astronomical unit is 1.5 times 10 to the 11 metres. 1 arc second is 1 over 3,600th of a degree. And converting to radians, we get this. So 1 parsec equals 3.1 times 10 to the 16 metres. So when using the formula, remember, either you are measuring little d and capital D in metres and alpha in radians, or you're measuring little d in astronomical units, capital D in parsecs, and alpha in arc seconds.